Today we are going to talk about fluid mechanics. Following is a table of contents. First is brief introduction of Bernoulli's equation. Then derivation of equation and relationship with Navier-Stokes equation. Lastly, the history and application of fluid mechanics. Bernoulli's equation was published by Daniel Berzelius in 1738. It relates the velocity, height, and pressure of fluid that follows a streamline. The equation looks like this. It can be taken as conservation of energy in fluids. Next is the derivation of equation in two ways. First way is from what we all know. The other is by calculus. This is the equation for the conservation of energy. If we divide it by volume, it is still constant. Volume is area times distance and density is volume divided by mass. From that, we can get the following equation. Force divided by area is pressure. Then we get the Bernoulli's equation.
Next is derivation using differential. This is a free body diagram on a small part of the streamline. The Bernoulli equation assumes that the fluid moves along the streamline, so we only need to consider the force in the s-axis. For convenient calculation, we set the coordinate with streamline as one axis and placed n and y-axis perpendicular to it. The s-direction pressure on the fluid is p dn dy and p plus dp dn dy. The velocity of a fluid is subject to position and time as variables, but since Bernoulli's equation assumes steady state, it is independent to time, so v is subject only to s. We'll first find the net force. Mass is the product of density and volume, and acceleration is expressed using ds because v is a function of s. This net force is equal to the sum of the pressure and weight applied to the fluid, because there is no shear stress. The s-direction weight can be expressed using the sign as follows. If we organize it, we get the following equation, and we can change s sine theta into z. Integrating this expression along the streamline yields the following expression. Because we assume an incompressible fluid, we can take the low out, and we can say that the equation is constant because the same type of expression comes out for all characters. In deriving the Bernoulli equation, we made the following assumptions, and Navier-Stokes equation deals with the general case without these assumptions. Therefore, we can deduce about Navier-Stokes equation with these conditions. The viscous term will be added, and vector operation is required because it is not fixed in one direction. Below is the Navier-Stokes equation under incompressible conditions, where the left side is differential for position and time for the velocity u of the fluid, and W is difference between the local pressure. G is the acceleration due to external forces, and the last term is the viscous term.
Next is the history of fluid mechanics. The beginning of fluid mechanics dates back to the 3rd century BC. Archimedes of ancient Syracuse measured the density of objects using buoyancy acting on objects submerged in stationary fluids. This is the Archimedes principle that we often think of when we hear the word eureka. Later, in 17th century, Newton proposed the laws of motion, and in 1755, Leonard Euler applied these laws to fluid flow to derive the Euler equation. The Euler equation is a differential equation for the matter-time derivative describing the change in momentum of a fluid with no shear stress. The form of the expression is as follows. In 1738, Daniel Berzelius also presented the Bernoulli's equation, which was applicable to the flow of ideal fluids. Meanwhile, the contemporary Jean-Long d'Alembert assumed that the fluid was stationary and non-compressive and viscous, and developed a formula for the situation in which an object moves at a constant speed inside the fluid. As a result, we found that the sum of the forces that an object in the fluid receives is zero. This means that there is no resistance to object that crosses the fluid. For example, when the balloon crosses the air, there is no force on the balloon, so it shouldn't move in the wind. This discovery leads to the result that contradicts everyday experience and is now called the d'Alembert paradox. The reason this paradox occurs is that there was a large difference between the actual fluid and the ideal fluid that assumed various conditions. In some cases, the Euler's equation's results may be constant even when assumed to be an ideal fluid. But as the action of viscous forces is inevitable in most real fluid flows, the assumption of ideal fluid causes contradiction. It was the Navier and Stokes equation in the 18th that solved this problem. The Navier-Stokes equation made it possible to consider the viscous effect by including the shear force in the Euler equation and solved d'Alembert's paradox. But because Navier-Stokes equation is a non-linear partial differential equation, it was so complex that it couldn't get a general solution. And as a result, it developed into the current computational fluid mechanics.
First, fluid mechanics is utilized in CG. The realistic CG seen in movies and animations is related to the Navier-Stokes equation. Stanford University computer science professor Ron first utilized the Navier-Stokes equation in 1999 to create CG simulations, starting with this equation being used in various movies and animations. The exact solution of Navier-Stokes equation is not found, but in CG, visual effect is more important than accuracy, so we can give a realistic enough description with an approximation. Computational fluid mechanics was developed to solve Navier-Stokes equations through discretization and numerical analysis techniques for space and time. Simply put, it can be understood that computational fluid mechanics is a technique for obtaining precise approximations of the Navier-Stokes equation to determine fluid flow. In the past, there was no way to interpret fluid motion except for experimental based methods, but advances in computational fluid mechanics have enabled computer simulations and saved time and money. The phenomena related to the flow of fluid around us can be easily observed. Computational fluid mechanics is used in a wide variety of fields, and it's used in almost everything from aircraft and automobile design to the spread of pollutants to weather observation. Lastly, fluid mechanics used in airplanes. There are four forces on the plane: lift, drag, thrust, and weight. Among these, lift is the force that is directly involved in making an object float in the sky. To fly a plane, you just have to make the lift greater than gravity. So what fluid mechanics is applied to an airplane? This picture is a section of the wing of airplane. As mentioned earlier, Bernoulli's equation said that velocity and pressure are inversely proportional, when the air flow and the speed changes, the pressure changes. Pressure will be lowered around the upper section of the wing where the speed has increased, and opposite for the lower section. Because of this, a net force will act on the upper direction of the wing as a whole, and because of this, a lift will occur and plane will float upward. A certain level of lift must always exist on the wing for an airplane to be airborne, and a lift coefficient is required to calculate the lift, which is the value obtained by the experiment, which can be calculated. The main reason for this pressure difference is the viscosity of the air, and when the fluid flows around the curved plate, which means pressure gradient is not zero.